Okay, welcome to Robotics 2. So we are talking about state estimation. State estimation is a very important topic. And so far, what we talked about is we talked about how do I find out the values of roll and pitch based on the accelerometer measurement. And as you can see, there are three equations. These three equations are highlighted here, 1, 2, and 3. These three equations give you the value measured by accelerometer in x direction, y direction, and z direction. So please note, there are three equations and there are two unknowns, theta and psi. Once again, there are three equations and two unknowns. So you can find the value of theta and psi. Theta and phi. Theta and phi, so which is pitch and roll from these equations. So you can find out the value of pitch and roll. Unfortunately, as you can see in these three equations, psi, which is the heading, is not present. So it cannot be found out. But what you can do is you can use compass and find out the difference between the magnetic heading and the actual heading, use the correction factors, and then find out where you are headed. But with magnetometer, the problem is if you are in the vicinity of ferromagnetic objects, the magnetometer would deviate. It will have soft ion and hard ion errors. And yes, at the end of the class, I will go over project 7 and answer questions you may have. Okay, we talked about model inversion, and these are the two angles that we get. Theta, which is the pitch angle, and psi, that is the roll angle. And you can use a GPS signal. So for an example, from the GPS, you are gonna get pseudo ranges, and you can run through a low pass filtering. LPF stands for low pass filtering, and then find out the values of north direction, east direction, course angle, chi, and the ground speed. Once again, ground speed is air speed plus wind speed. Now, if you look at the old receivers, they used to be very slow. So they used to give us once update per second. So that's why it was 1 hertz. But newer GPS receiver, the commercial GPS receivers or hobby GPS receivers can go all the way up to 20 hertz. And some very expensive GPS receiver can get slightly higher update rate as well. Now, once again, what you can do is you are going to have jagged estimates. So you will have to smoothen those estimates. And unfortunately, with GPS, you are never going to get an accurate measurement. You will have some error present. And what we plan to do is we plan to use some sort of smart signal processing algorithm that will minimize the error and give us sort of an optimal solution all the time. Now, the next topic that I'm going to discuss is super duper important. So I want everyone to pay very close attention. I am going to go very slow, but please understand this material is super duper important. So super important material. Now, the first question is, what is an observer? So many a times, so you have a measurement. So if you have a measurement and you have an observation. So there is a difference between measurement and observation. For an example, if you are trying to measure the value of theta and you have a super duper accurate instrumentation that gives you value of theta directly, then that's a measurement. But many a times theta may not be directly available. It may be embedded in some other measurement. Say, for an example, you have to use a mathematical relationship and find out the value of theta, or you have to use some other indirect way to measure. So observation is sort of indirect and usually not super accurate. So observation is you are trying to get an assessment, or you are trying to see what the measurement is, but you are never gonna get an actual measurement. You will have either noise, so measurement would be fluctuating, or you would have drift, which means the measurement, even though ideally the measurement is constant at say 30 degrees, but you will notice that your scale is drifting slowly. So the idea is we don't have direct way to get this true value. So what do we do? What we do is we try to construct something known as the observer. Now, what is this observer? And this observer, let's start with a very simple system dynamic model. And what I'm going to do is I will explain this in an alternate slide, but this is the system dynamic model. AX, A is the state matrix, which is multiplying the states. B is the control input matrix multiplied by control input. And Y is equal to CX. C is actually, this is what you are getting. So this is the output. So now what we want to do is somehow we want to use this state equation to come up with some sort of approximate approximate estimation on the observation. So what we are going to do is we are going to construct something called as an observer. What does this observer do? This observer's sole function is somehow to approximate the measurement using some sort of observation. And clearly, this is not going to be accurate. So what I'm going to do is I'm going to write down an equation. And this equation, I will try to explain the concept of observer. And please understand, this is a super important concept. Now, let me give you a physical interpretation of what an observer is. So you are here, okay? And you see your friend walking. You see your friend walking. And what you want to do is you want to find out how far is your friend from your current location. So what is the distance? The best way to do that is use some sort of a range finder or a laser finder machine, point it on your friend and exactly get the distance. But unfortunately, that is not possible. So what you can do is you use maybe a post. and then you use some sort of other landmark. Unfortunately, you do not know the exact distance between these two. So exact distance is not known, but approximate distance is known. So what you can see is if you were to time it at t is equal to t0, your friend is at this post or maybe a water hydrant. And then he goes to the second landmark at t1. You find out the time difference. You know the approximate distance. So you can find out v approx, which is distance divided by t1 minus t0. So you can find approximate time. And then you have some estimate on the velocity. So you know how fast this person is traveling. That gives you an estimate on that person's velocity. And then what you can do is you can approximately estimate. So this is very important. You can estimate where person B is, location of B. Unfortunately, you do not know the distance between yourself and your friend. You can come up with some sort of approximate guess number. Then you have an approximate location of your friend. This is nothing but a principle of observation. So with this approximate velocity equation, you can find out the approximate distance, and that kind of gives you estimate on where your friend is going to be as time goes on. Now let's start with exact system. So we have a system model, and this system model is exact. And I'm going to write this equation down. X dot is equal to ax plus bu, and y is equal to cx. Now, what we want to do is we want to construct an observer model. So I'm going to construct an observer. So what is the function of this observer? The function of this observer is to come up with some sort of approximate model. So I will estimate this like x dot is equal to a x hat plus bu plus. Now I'm going to add a matrix L y minus c x hat. Now this is the equation for the observer. What this means, this is the original model, and this is the correction due to sensors. Some of you may think, oh, this equation looks super complicated. But actually, this equation is not super complicated. What I want you to do is, I want you to take this system model. I want you to take the system model, and instead of x dot, substitute x hat, and substitute x hat dot. So check this out. This equation now going to become ax plus bu and y is equal to c x hat. Now what is this? This x is s. In other words, your friend's actual location is given by the x, but your friend's estimated location is given by x hat. Now the question is, how do I append this equation? So if you look at this equation, what I'm going to do is I'm going to construct the error. So if you look at the error is the difference between actual minus estimated. So actual minus estimated. And think about it like this. You have some error. The error is between actual and estimated. If my error is zero, that means my estimate is close to actual value. If my error is zero, then my estimate is close to actual. But in regular practice, that may not happen. In regular practice, that may not happen. So what I'm going to do is I'm going to go ahead and subtract the equations, the actual equation and the observer equation. And when I subtract, I do this subtraction, please understand some interesting things happen. And these interesting things give me an equation for error. This is rate of change of error. So error d by dt of error, and I'm going to call it x tilde, is equal to a minus l c x tilde, which is nothing but a x tilde minus l c x tilde. And if you look at x tilde is nothing but a x minus x hat minus l c x minus x hat. And I want to do a small change here, and this is super important. Everyone just pay attention. This becomes a x minus x hat minus l. Then if I take c inside, this becomes cx minus cx tilde, and this equation is a x minus x hat minus l y minus c x tilde x hat. So estimate is the estimate of the sensor value. Estimate is the estimate of sensor value. Now what I want to tell you is, I want you to look at this equation and observe that this equation is the equation for error. This equation is the equation for error. What that means, and I want to be very clear about this equation. So let me add a new slide and explain what this error thing means. So you have an error, rate of change of error d by dt is equal to a minus l c x tilde, or x error. I will call this x error. So this is, now a comes from the system dynamics. A is system dynamics. C comes from the system equations. So observations that are measured. L is nothing but is a matrix that you choose. So this is something that we choose. So what happens because of this L? If you think about it, this expression, it's same as the equation that we have seen multiple times. So I'm going to give you an equation, say x is equal to x dot is equal to ay. So if eigenvalues, if the eigenvalues of A minus LC are negative real or in the left half. So we talked about it. This is the imaginary plane. This is the real plane and have negative real values. Then the system error dot is equal to A minus LC E is asymptotically stable. What that means is as time goes on, the error will go to zero. What that means is as time goes on, your estimated value, which is x hat, and if this is your actual value x, it will go down to zero and it would converge with the actual value. And that is the fundamental reason an observer is used. So once again, what is an observer? So observer is used to estimate the state. If observer dynamics equation has negative real parts, then as time goes on, the error goes to zero, which means observed value approaches true value. And this is the fundamental purpose of observer. So you have an observer equation, and once again, I will try to explain this. Yeah, Zubair, your questions are very good. So there is an observable. So basically, what it means, let me answer this question. All this is good if you are able to see your friend. Imagine if there is a tree. If there is a tree and you are not able to see your friend, then you don't have observation. So in that case, what you do is you do something called as the prediction, which means based on previous observations, you have an approximate motion model for your friend. And you use that motion model to estimate. And as soon as, by grace of God, if you see or if you get an observation, you validate that observation. So you use something called as prediction. And sometimes even the prediction is not possible. So what you do is you resort to random signal theory and stochastic estimation theory, wherein you introduce additional variables that are stochastically varying and then get an estimation. But at this point, what we are saying is everything is observable. But if there is no, if you cannot observe, or if you have partial observer, there are different excellent schemes for estimating the measurement. But let's start with the very basic. So the very basic idea is I don't have the direct way to get measurement value. And what I'm going to do is I'm going to use an alternate way to get the measurement. And the way I do that is by means of something called as observer. And observer dynamics is nothing but constructed with the difference in the state dynamics. So what I'm going to do is I'm going to use this observer equation to observe the variable. And as long as this observer dynamics, as long as that error goes to 0, then I can say that my observer is able to track the original state accurately. So what I want to do is, there is something else. How do I make, okay, before I proceed any further, I just want to make sure that this concept of observer is clear. So Zubir, when observation is not available, you can use a predictor model or a mixture model and then actually come up with estimation. But before I proceed to the next part, I just want to make sure that we understand what is an observer, what is the purpose of an observer, and how is this observer constructed. Any questions here? So now what we are going to do is we are going to design something called as dynamic observer. What that means is this observer is dynamically changing. Now I want to give you the same example here. What do I mean by dynamically changing observer? So think about it, that you have say some sort of a telescope, okay? And what you are doing is you are using this telescope to see where your friend is. Now, dynamic observer means you are changing the focal length of the telescope so that you can observe your friend clearly. Obviously, depending upon where your friend is, whether your friend is here, whether here, you need to make some adjustments to your telescope so that you can observe your friend correctly. And that is the fundamental principle of dynamic observer. In other words, we want to make the changes dynamically so that we can tune our observer sort of in an optimal way. We'll try to get the best possible estimate. Everyone understood this? So let me go to the next part, and I may have to go back and explain the observer in connection with the dynamic observer again. So let's do that, because Kalman filtering is super important and often a point of confusion, but it's not. We'll try to discuss that in super simple way. So let's try to understand now. What we have is we are going to use something called as the predictor corrector system. So what I'm going to see is I'm going to assume that my friend here, that friend is at location B. Sometimes I can observe him, sometimes I cannot. So what I'm going to do is I'm going to use some sort of a prediction scheme. So what I would do is, in between measurements, when my friend is not visible, I have an approximate velocity model of my friend. And I will use that model to come up with some approximate value. And as soon as I am able to get the measurement, so here the friend is not visible, so not visible, but I know approximate velocity. So from approximate velocity, I can find out approximate distance. But I clearly know that this is not correct. But as soon as I can observe, as soon as my friend is visible, I can correct. What I can do is I can correct this estimate. So there is something called as posterior and prior. So what it means is you have a previous estimate. You are going to use this correction. So this is the correction. And you are going to find out the new, supposedly better estimate. New estimate. And at this point, we are just dealing with estimate. So yes, Joseph, it's due not today, but on April 1st. Okay, so one thing I want you to understand is we are using the predictor and corrector system. What it means is we have a dynamic model, and this dynamic model is used when actual measurement is not available to come up with this estimate. But this estimate is corrected as soon as the actual value, this is the true value or true measurement. So this is the measurement is available. And what we do is this L is gain is chosen in such a way that this new estimate is updated with the correction factor. And with this, what's gonna happen is you are gonna get a better estimate. And for nonlinear system, the idea is exactly the same. And let me estimate or let me explain this in simple words, because this concept is super simple, but sometimes math is going to be tricky. So here is the thing. Here you are. This is at location A. Your friend is at location B. And your friend starts walking. And this is the milepost 1. And this is the milepost 2. And what you have is you have a telescope. And you have a stopwatch. So you have a stopwatch. So you can approximately know where your friend is and where your friend is at this location. But imagine in between, your friend goes past the tree. So certain period of time, your friend is not visible. So what you can say is based on the previous measurement, say this is the milepost 0, based on the previous measurement, you know approximately the velocity at point V1. You know how much time it passed when this friend crossed this tree when actual measurement was not available. But since you have the time, you can actually multiply velocity by time and approximately find where your friend would be. This is what you found out from your approx analysis. And this is nothing but X prior, which means basically this is what you came up with the dynamics. However, as soon as this friend emerges from this behind the tree, you notice this friend is actually over here. And this is actually the true value, or this is the Y where the friend is. So now what you can do is your approximate analysis gave you X hat, but your actual value was Y. So now you have a correction. You have this correction that needs to be applied to the original estimate. So as you can see here, I want you to carefully observe this. This is the prior. This is prior. This is prior. So this value and this value is the same. But as soon as you get new measurement, you correct your prior. And the hope here is with this correction, you are gonna get the better value of the estimate. Now, some of you may ask me this question: why this jugglery? If we know at this point our friend is here, then why not to use the value of y? And here is the problem there. Sometimes you may not be confident on your ability to see your friend at point 2, which means you may have some parallax error, or you may have some sort of visibility error. So you do not know if this y you notice is accurate or not. So at this point, we do not know whether this y is accurate. We know for sure our x hat is not accurate. So how do I combine, or how do I fuse, or how do I merge these two inaccurate measurements in the best possible way so that I get sort of an optimal solution? And that is the whole purpose of this scheme. Now value of L, sometimes it is fixed. This is called as the gain. Or sometimes it is changing depending upon whether your measurement is accurate or whether your estimate, the previous estimate, is accurate. And that is the fundamental principle of Kalman filtering. So what I'm going to do is, here is what is happening. So you start measuring. So as you can see, you see your friend and you estimate your friend is going somewhere here. And all of a sudden, boom, you see your friend at this location, and then you make a correction. And then you continue with that correction. You have another measurement at T3. You make this correction. Then you go back at T4, you get an update. And what happens is, with this scheme, you are periodically correcting your measurement. It is exactly similar to what we talked about in GPS. As you know, the IMU is drifting. Every time you get a GPS update, you correct it. But the problem here is the GPS update is not super duper accurate. So somehow you need to combine these two inaccurate measurements and come up with a good estimate. Okay, a fair warning, equations that you are going to see in this next section are going to be super duper complex. And it may be a little difficult to understand the complete Kalman filter in one go. So you may have to go back and review this material again. But understand, equations will be implemented in MATLAB. As a matter of fact, MATLAB has a Kalman filter block that we are going to use to see the actual implementation of Kalman filtering. So I will explain the equations, and then I will show you how to use the Kalman filter with an example. So Kalman filter follows the same dynamic observer process. But what it's going to do is, it is going to improve the quality of estimate by propagating an error covariance matrix. Now, first and foremost, what is covariance? Covariance means how property A is related with property B. So for an example, if property A increases and property B increases, they have some sort of correlation. So they actually are codependent. So there is covariance. So what we are going to do here is, we are going to receive the measurements at every period of time. We are also going to get the error, and then we are going to see how that error is changing as time goes on. And we will update our gain value based on that error. Now, there is something called as the quadratic forms, and quadratic form is nothing but a simple equation, which is something like x1 square plus x2 square. This is a quadratic expression. This is something similar to a quadratic form. If I write this in some sort of a matrix equation, then I can write this as x1, x2, 1, 0, 0, 1, x1, x2. So if you expand this equation, you will land up with this equation. So this is the quadratic form. Multivariable Gaussian. This is how the measurements are varying. So as you can see here, there are two variables. There is x and there is y. And x has this Gaussian distribution, and y has this Gaussian distribution, and x has this Gaussian distribution. Now, if you see their interdependent relationship, so how x is dependent on y, and if you were to plot those together, you will see this type of a blob. Now, there is a lot of probability theory that is used in Kalman filtering, but I'm not gonna go through the details. What I would do is I will send a link to something called as the Kalman filter videos, and that will give you a very good understanding of the theory behind Kalman filter. But here is what Kalman filter would do. What you have is, there are something called as regular Kalman filter. So Kalman filter. There is something called as extended Kalman filter. And there is something called as uncentered Kalman filter. And for each filter implementation, there is a Simulink block, and we will use those. But fundamentally, let's start with a linear Kalman filter. In linear Kalman filter, you have a linear state equation and you have noise. You have linear state equation and you have noise. And you have the observation or output that also is noisy. And there is also some noise. Now, what I want to do is, I want to use this observation to come up with some type of estimate. Now, there is something called as measurement covariance, which means how the measurement changes. And then there is something called as the process covariance, which means how the process itself changes. So there are these two stochastic parameters that are present in Kalman filter. When you look at the Kalman filter derivation, there is something, a prediction step, and there is correction step. Just like the equations we saw, wherein you had an observation equation that is being used to correct the estimate, something like that. What you do is, you have an estimate, you get a priori estimate, and then correct it with the observation. However, there is additional step here. You find out the estimation error. So this is important part. You find the estimation error and you find the covariance of estimation error. And depending upon the error properties, what you do is you tune the Kalman filter gain. And this is the dynamics of the Kalman filter. This is the derivation of Kalman filter. And again, these are the correction and predictor equations. And again, you can go through these. Then there is something called as measurement. There is update. Then there is covariance update. And then finally, what you do is you get these equations. Now, some of you may say, wow, a lot of equations. So what I'm going to do is I'm going to explain how all these equations are implemented inside MATLAB. Kalman filter is a topic. People have done their, or students have done their PhDs on Kalman filter and different implementation of Kalman filter with different noise models and so on. So what I want to show you is, just remember Kalman filter is a mathematical algorithm to come up with the good estimate. And now I'm going to show you how to implement Kalman filter using MATLAB. So I'm going to start sharing my screen. And go to Simulink. And I just want to show you another good resource, Kalman filter MATLAB. So here is the resource on what Kalman filter is and how it is done using MATLAB. And I would encourage you, and I will put this in the chat window. I would strongly encourage you to watch these webinars that will give you a good understanding of why Kalman filter, what is a state observer, what is an optimal state observer, how is that estimation works, and how to use Kalman filtering. So I would actually add this link also to the our course website. But now I want everyone to go to Simulink model. And in Simulink model, what I'm going to do is I'm going to open Simulink. And open Kalman filter.rar. Expand that and see the Kalman filter example. Here, the first example is Kalman filter XLS. So I want everyone to open this file. And when you open this file, I want you to observe something. First and foremost, this is a state space block. This state space block is 0, 1, -1, 0, 0b, 1, 0, 0, pi by 18, 0. These are the initial conditions. Now, when you run this, I want you to observe, when you run this, you get multiple plots. This is the point where your actual output, so the file announcements, yes, the files are in announcements. So what I want you to do is, I want you to track this scope. Here you see a yellow line. This yellow line is actually the true value. This yellow line is actually the true value. Now, there is this noise that this true value is actually corrupted by this noise source. This true value is corrupted by this noise source. And what happens is, once you corrupt this true value, you get this noisy value. And as you can see, I want you to pay close attention to this scope 2. Notice this scope 2 is super duper noisy, which means this scope is nowhere close to the original signal. So what it means is, if I were to use some sort of sensor that is noisy to measure the output of this system, I'm going to get this output. And clearly, this is not the correct output. Everyone understood this? Now, what I'm going to do is, there is something called as Kalman filter block. Go to Simulink library browser, say Kalman filter. And once you click, you should see Kalman filter in system toolbox. You should see in system identification toolbox. Can you look? Have you located Kalman filter block here? So you can actually grab this block and drop in the canvas. Now this Kalman filter block has actually two inputs. One is U, which is actually the input to the system. So you can track it all the way from here. And Y is nothing but observation. So our observation is this noisy thing. So this is observation. And once I feed, now let's double click on Kalman filter block. When you click on Kalman filter block, you can specify the values of Q, values of R, and values of N. Let me just explain what Q is. Q is the basically it's a Gaussian process. So which means you will expect some sort of statistical variation. So you have something called as the process noise and something called as the sensor noise. So Q is nothing but the process noise, and R is nothing but sort of the measurement noise. So remember this, R is the measurement noise and Q is the process noise. Now, estimation of Q, process noise, is difficult, but estimation of R is simple. So for example, if you have a sensor, what you do is you acquire data from the sensor, and you will notice that sensor is not going to give you a clean signal. It will be varying. And what you do is you capture that varying signal and find out the standard deviation, and that gives you the process noise. I'm sorry, measurement noise. So please note, there are two noises. One is the process noise and one is the measurement noise. So Q is the process noise and R is the measurement noise. Next, I want you to go on to options. In here, if you look at, you have additional inputs, wherein what you can do is you can input the actual input value. You can add control measurement value. You can take this off. As if you take this off, then you can just feed the measurement. You don't have to feed the input. And then what you do is you add a scope block here. Now what's going to happen is, once you run this, you are feeding a noisy measurement, and Kalman filter has you need to specify the system dynamics. How would you specify the system dynamics? So you will specify the system dynamics with individual A, B, and C matrices. Our A matrix is 0, 1, 0, 1, let me see, what is it? 0, minus 1. 0, 1, minus 1, 0. 0, 1, minus 1, 0. Our C matrix, let's see what our C matrix is. 1, 0. It is 1, 0. Let's see our D matrix. D is 0. D okay, since there is no input, it's not asking for D matrix. If you go to this, if you go to options, if you click input port, then it will ask for C and D matrices. So you have B matrix, 0, 1, and you have D matrix. So please note, if you add this input port, then you will have to specify all the 4 matrices. If you take your input port out, double click, then you see you have to only supply A and C matrices. And what I'm going to do is I'm going to feed the output of the Kalman filter block to this scope, run this, and I will see the output. Now, here is the problem. There are 2 ways Kalman filter is implemented. Either you can implement Kalman filter on a discrete system, or you can implement Kalman filter on continuous system. So we are feeding the data that is continuous. So we can't use the discrete time Kalman filter. We have to use continuous time Kalman filter. Click OK and then run, and you will notice you will have this output. Now, some of you may ask me, why 2 outputs? Please note, we have 2 states, x1 and x2. So this Kalman filter is giving me the values of both the states. And however, for comparison purposes, I'm just comparing the first state with the output, and this is how the Kalman filter gives me the result. So here is what is happening. If I were to use the sensor measurement, just sensor measurement, this is what I get. And I can't figure out what is the true value. If I use a Kalman filter, it gives me a better estimate of the true value. And that is the fundamental function of a Kalman filter. So what Kalman filter does is Kalman filter takes a noisy output and it actually has an estimate on the process noise, and it has an estimate on the measurement noise. It combines these 2 noises and then gives us an output. Everyone understood this? And I will give you a minute to run through this simulation. And some of you may ask me, what is this model? This is nothing but the model for a simple spring mass system, no damper, just spring mass system. So you have a spring mass system, you are supplying some input condition, and that is giving you an output. In one case, because of, since we have measurement that is noisy, we have this variation, and Kalman filter is giving us an optimal estimate based on the noise properties that we substituted. Any questions here? So if you look at the equations, what did I do to fix the error? If you click on Kalman filter, there are 2 ways Kalman filter is implemented, either in discrete time or in continuous time. Our data is continuous, so we need to use a continuous time Kalman filter. There is other way of doing this. You can change or you can convert a continuous system into a discrete system. So the way you can do that is go to library browser, and then you will see commonly used blocks, continuous, discrete, and there is something called as 0 order hold. You can grab that block, 0 order hold, put it over here, and now what will happen is with this 0 order hold, you can convert a continuous system into a discrete system. Now you can go back, convert the Kalman filter into discrete, and then run. And then now you have your output, which is the output of the discrete Kalman filter. And now you will see that these are actually points. This is not a continuous signal. That's why you have so lot of variation, because these are now points. So this is like a discrete approximation of the continuous signal. So there are two ways to do this. Either you can add zero order hold, convert continuous system into discrete system, or just go back, take the Kalman filter block and convert it, use a continuous time Kalman filter. And you can run. Any other questions? Now, one question that comes in mind is, what if I do just simple low pass filtering? But before I answer that question, I just want to make sure everyone got this value. You can actually change this a little bit, which means you can go to library browser, go to continuous, commonly used blocks. You can go to sources, and now you can add sine wave. You can add a sine wave here. So now you have not a zero input, but a sinusoidal input. Here you can go to options, you can add a port U and then feed this sinusoidal input to this port and run. And again, see. Now, yeah, Borna, answer that question. Just a second, bear with me, just a second. Now you can see that this response is increasing because this sinusoidal excitation is resonant. The frequency of the excitation is same as the frequency of the signal. So I'm going to change this to say 0.5. Click OK, run, and now you will observe that, check this out, you have estimation and you have signal. Now you would notice that the Kalman filter is not able to track the output very accurately, because right now the system excitation is quite high. So what you need to do is you will have to adjust and tune the system only then, or tune the Kalman gains, or tune the noise covariance and other parameters, so that you will get a reasonable estimation. So this is, do we need one of these? So when you have a noisy measurement, so, and I think that is part we have to do in the next iteration. When you have gyroscope and accelerometers, they are not going to give you clean output. The output from gyros and accelerometer is going to always look like this, shown in scope 1. So somehow we need to filter it. So Kalman filter is one way of filtering it. What Kalman filter does, essentially, it takes the Gaussian of the measurement noise, it takes the Gaussian of the process noise, it multiplies those two Gaussians, and then you get a resultant, and it finds the mean of that resultant. All that information is very well explained in these webinars. So I would strongly encourage you to go through these webinars. There are just 7 parts, and that will make your understanding of Kalman filter much clearer. But as we talked about, the equations for Kalman filter are quite intense, but practically this is how we will implement the Kalman filter. The next part, which I want to show you real quick, is what if I use a simple filter. So next part is KF example 2. Please open. Yeah, there are libraries. Even if you use Arduino, there is a Kalman filter library. If you look at Android or iPhone, there are Kalman filter libraries. So here is something else. Now, how would I implement a low pass filter in the Simulink? And this code shows you the implementation of a low pass filter. So if you go to library browser and if you say low pass, so basically what it will do is all the low frequency content will be passed. So low pass filter, and I'm going to search. Oops. Yeah, I think they need to be low pass filter. Search. Okay, so you have multiple types of low pass filter. I would recommend using this low pass filter in the DSP toolbox. That is what I used. So if you click on the low pass filter, it will ask you what type of filter you want to design. There are two types of filter: finite impulse response and infinite impulse response. And then it will ask you what is the pass band age frequency, what is the stop band age frequency. What this means is all the frequencies beyond 4.5 hertz will be chopped off. What is the pass band ripple? And if you want to see how this filter is going to work, you can click on view filter response. And yeah, so view filter response, apply, and then it can actually generate a filter response. Let me explain to you real quick what this filter response is. Okay, if you see the filter response, this is what it shows. It is going to allow the signal from 1 to 4.5 hertz. So it's going to allow the signal as soon as it crosses 4.5 hertz, all the signal will be attenuated. All the signal will be blocked. So this is how the filter is going to respond. So all the low pass frequencies will come through, but all the higher order frequencies, essentially noise, will be blocked. Now what you can do is you can run this Simulink script. You can run this Simulink script and then observe the response. And you will notice that even after low pass filtering, the system does not give you or low pass filtering does not give you good response. On the other hand, this scope is comparison with Kalman filter. As you can see, the Kalman filter is tracking or giving you the input or a true state very accurately. So if you have noisy signal, sometimes people say, just go ahead and do a low pass filtering. That may work sometimes, but not always. So Kalman filter is sort of an optimal filter. So compare this scope, double click on this scope. You will notice yellow line is the true signal and the blue line is the output of the Kalman filter. On the other hand, this is the actual measurement. This is super duper noisy. This noisy measurement, when I filter, I get this output, which is filtered, which is less noisy, but nowhere compared to the true value. Everyone understood? So now I will try to answer, I have 4 minutes. I will try to answer the question on project 7. So tell me, what questions do you have? Any questions on project 7? You are welcome to raise your hand or type. There is a lot of change. Or do you add the pitch loop? Yes, you will start with the pitch loop and then add stuff to it. So you'll start with the pitch loop. And then add the blocks on the left and on the right hand side of the pitch loop. Does that answer your question, Travis? Okay. Any other questions? Your VR max. So if you think about it, okay, let me answer John's question and then I will answer Anson's question. So VR max, you can use 10. That's totally fine. So you can use VR max. So 10. To answer Anson's, yes, same with delta R max. So this is sort of an extension of the trimming problem that we already solved. So whatever trim values that you have, please use those values. Airspeed model, since my beta 2 is 0, so that there is no response from the system, since Sagi is normal. Okay, so which question are you referring to, Anson? You mean 6.6? In 6.6, airspeed from pitch loop. Yes, airspeed from pitch loop. And which figure are you using to implement airspeed from pitch loop? I am presuming you are using figure 6.18. So airspeed to pitch. I'm assuming you are using figure 6.18. Now in that, okay, good. Does that answer your question or do you have any other specific question? Anson, are you good? You have, okay, all right. Any other questions from anyone? Okay, what is 6.8 asking? Oh, I did not ask you to do 6.8. So, because once everyone is done with this exercise, I'm hoping that I would show you how this whole thing comes together. So, signal generator for 6.6. You can use a step input for signal generator for 6.6. which is similar to the example that I worked out in the class. Okay, just does that answer your question, Ghazi? Okay, so to answer Borna's question, 6.8 is actually what you want to do is you want to combine everything together, and I will try to show you how that script would look like, but it's a little complex, so I did not ask you guys to do it, but I will try to show it to you. Let's see. So project 6 files. So what you need to do is you will have all these loops running together. Then you will have to compute the gains, and then let me see, you will have the total solution. It's not here. Robotics 2. Just bear with me for a second. Robotics 2. Ideal robotics. Project solution. Project solution. And you will have chapter 7. So you will have something like this, wherein you will have your MAV dynamics, all your loops are implemented in this autopilot function, and these autopilot function actually implements all the lateral and longitudinal loops. This autopilot takes the the feedback from the actual state that's get fed into autopilot. And what you have is you have here the commanded airspeed, commanded altitude, and commanded course heading. And this you specify these values. Autopilot converts those into appropriate commands. The elevator deflection, the rudder deflection, and aileron deflection and thrust sends that to MAV dynamics, and then MAV dynamics sends out to the draw aircraft. So you have this MAV dynamics equation, which is again the exact same thing as we talked about. You have forces, you have dynamics equation, but I added one more block wherein what you do is you take the sensors, the data from the sensor, and then actually display the sensor value. So this is the complete the autopilot simulation. This is how it would look like. So you can actually set a particular airspeed, and then this script would run, and it will actually show that in the presence of the wind disturbances, your aircraft is flying at the commanded airspeed, commanded altitude, and commanded course. Does that answer your question, Borna? But that is a little complicated. So that's why this is, I have not asked you to work on this, but I plan on showing this to the class once everyone got all the transfer functions and controllers working. Okay, that's it for today. I'm gonna stop recording.